So I've already, I hope, convinced you of the first couple of points here, that when we're talking about dark matter, it's not gas. It's not something like you counted the number of stars wrong because some of them were too dim. It's not mostly planets. There are a lot of planets out there which we're now discovering, but it's not nearly enough to talk about this. One not so obvious point is that it's not mostly neutrinos, and in this I'll show you why we think that's true. But you would have thought that neutrinos is a very good idea to explain dark matter, because neutrinos are an elementary particle that we know about. They exist. We studied them in Fermilab. They are invisible for the most part. They're very, very hard to detect. They hardly interact at all with ordinary matter. And there's lots and lots of them out there. So they're hard to detect. There's lots and lots of them out there. That sounds like a good candidate for dark matter. And in fact, they are part of the dark matter. They're a few percent of the dark matter, but they're not most of it. Another thing you might have thought of, and in fact, I've got this question a lot, it's a very good question, is, well, maybe most of the dark matter is black holes. Because after all, we learn about black holes, we learn that the reason they call them black holes is that they're invisible. They don't emit anything. And black holes, we now think, do exist. There may be lots of them out there, so maybe that's the dark matter. This is not ruled out, but I think there's good arguments that most of the dark matter is probably not black holes. And one of the reasons for that is, the reason we've convinced ourselves that black holes exist is because stuff tends to fall into black holes. They have very strong gravitational forces. And when the stuff falls into black holes, the stuff emits light, things like X-rays. And that's the reason why we think, for example, that there's a supermassive black hole at the center of our own galaxy. It's not that we've seen it, because we can't see it, but there's a whole bunch of stuff falling into something in the center of our galaxy, and we think that something is a supermassive black hole. So that's, it's not completely ruled out that black holes could be most of the dark matter, but we think it's probably not. Well, if you buy all of that, what's left is some completely new kind of matter. So even more exotic than neutrinos, which is already a pretty exotic idea, would have to be the explanation. So let me explain why we think neutrinos are not most of the dark matter. Cosmologists, astrophysicists that talk about dark matter, they like to talk about cold dark matter and hot dark matter. This is a very strange terminology. When they say hot dark matter, what they actually mean is dark matter particles that are traveling close to the speed of light. So it's not what you would normally think of as hot. And when they say cold dark matter, they mean dark matter particles that are not traveling close to the speed of light. So that's what this really means. And although we don't have our hands in dark matter yet, you can make simulations of what dark matter would look like, how it would be distributed out there in the universe, by making certain assumptions about what the properties of the dark matter are. Like, is it hot or is it cold? And here's an example of what you get when you do these kinds of simulations. So these are in false colors to remind you that this is not supposed to be stars and galaxies. It's supposed to be the dark matter, how it would be distributed, and the galaxies would then tend to cluster around where the dark matter was. So it's not the galaxies themselves, but it's, if you like, the seeds of where galaxies and galaxy clusters should be. And then the only thing you have to ask yourself is whether the picture on the left or the picture on the right looks more like the universe we do see in terms of visible galaxies. And the answer, obviously, is the picture on the left. The picture on the left has the complicated structure that we see when we look out at galaxy clusters in the real universe. So we think because of this that the dark matter is what we call cold, meaning that the particles are moving, whatever they are moving fairly slowly. Neutrinos don't do this. Neutrinos, in addition to being very elusive and strange particles, they have very tiny masses and they move very close to the speed of light, even the ones that are out there in the cold universe. And so because of that, we think that they can't be most of the dark matter. And there's other data that we have now that pins this down quite precisely. So this simulation idea is now become a very powerful idea, partly because we have very big computers and we can do simulations sort of what the whole universe would look like, what its whole structure might be, given certain assumptions. So here's another example of a clue. This might not be right, but it's a clue as to something about dark matter. You could ask, well, suppose there is dark matter, how much does the dark matter interact with itself? Ordinary matter interacts with itself, right? That's what I'm doing right now. I'm ordinary matter and I'm interacting with you. Dark matter presumably interacts with itself through forces other than gravity. We don't know that, but let's assume that it does. Then I can do a computer simulation and say, what does the universe look like if I assume dark matter that interacts with itself with some force, some new forces that has some kind of strength. And then it affects how the universe looks, because depending on what those forces are, the dark matter will clump together in different ways. And then you just have to ask yourself whether, for example, the picture on the left, again, looks more like the universe we have than the picture on the right. And here again, the problem is that the picture on the right, which assumes dark matter that interacts a lot with itself, is sort of too smooth. The splotches in the middle are sort of too round. It's too regular. We don't see regular forms like that when you look out at the distribution of galaxies. They're all over the place in very complicated patterns. So this is a hint that the dark matter, whatever it is, it not only doesn't interact very much with us, it doesn't interact very much with itself. So this has led to what you might call the triumph of the WIMP, which is the name that Michael Turner, who is a famous cosmologist and is at this meeting, it's a term that he used to describe a particular set of assumptions for what dark matter is, which I've just motivated for you. That dark matter is some kind of new particle. Of course, there could be several kinds of particles. And that these particles are heavy. That gets back to the fact that they're cold, that they're not zipping around at the speed of light, almost the speed of light like neutrinos do. And that they interact, we know this for sure, they interact very weakly with ordinary matter, but perhaps also very weakly with their own kind. So this kind of dark matter is known as WIMPs, for weakly interacting massive particles. And so for the rest of this talk, I'm going to assume that the dark matter that we're looking for is WIMPs. So if that's wrong, then all the experiments that I'm going to talk to you about are going to fail, because they are designed to look for dark matter that is not only new particles, but are weakly interacting massive particles with more or less these features. So this is a problem in science. When you have a big mystery like this, where you don't know what you're doing, you can go down completely the wrong road and be in trouble. There are people that are designing other kinds and operating other kinds of experiments that will look at other assumptions about dark matter. So it's not that we aren't covering all the bases, but most of the experiments that are going on now, including all the ones I'll talk about, are looking for WIMPs. WIMPs rule the universe. So here's method number one. If there are all these WIMPs out there, dark matter filling up the universe, 5 times as much dark matter as ordinary matter, it must be raining down on us. There are particles of dark matter all over the place in our galaxy, holding the galaxy together. So they must be striking the Earth all the time. And you can figure out how often they're striking the Earth, because we know how much dark matter there is. And if you just assume that it's evenly distributed, which it isn't, but just to get a rough idea, you could assume that. Then you can figure out how many dark matter particles are passing through your body right now. So right now there are about 200 dark matter particles in your body. They're WIMP-like dark matter particles. They're moving at about 400,000 miles an hour. And that sounds a little alarming at first glance, but the good thing is that dark matter interacts very weakly. And so maybe once a day, once a week, we don't actually know yet, but very rarely do any of these dark matter particles interact with your body. Occasionally they do. Almost certainly, at least once in your life, a dark matter particle is actually given one cell in your body a mighty big kick. But again, that's not too alarming, because ordinary cosmic rays, which have nothing to do with dark matter, are also doing that. It's something that we just can't get away from. So dark matter is presumably coming in from space. It's going through everything. And now we just have to figure out, can we make a sufficiently sensitive detector to see those dark matter particles, to occasionally find one of them and make a blip somewhere. So that sounds like a simple idea. And here's a complicated looking slide that is also fleshing this out, and it's actually very simple what's going on here. So first of all, there's a whole bunch of weird names on this slide. Each of these is a name, most of them are acronyms, for a dark matter detection experiment that's going on someplace. So for example, CDMS, which is on the upper right there, which is the cryogenic dark matter search, is a dark matter search that's going on. I'll show you a picture of it in Minnesota with a lot of involvement from Fermilab, my laboratory, so it's one of the experiments that we're most excited about. But as you see, there are many of them, and they're all competing with each other. Everybody wants to be the first experiment to see, to really discover in a way that no one can deny the existence of these dark matter particles and to start to figure out the processes. So it is a huge scientific competition all around the world, all these different experiments. But the other thing I want you to see from this complicated slide is that these experiments are all making use of one or more of three techniques to detect dark matter. When a dark matter particle does interact with a piece of material, there's basically three things that it can do. It can deposit some heat in the material. It can make an electrical pulse in the material, or it can make a little flash of light material. And that's what these fancy words here in this triangle are saying. The ionization means it makes an electrical pulse. The, what does it say, phonon, that just means it deposits some heat light deposit. And the scintillation means it makes a flash of light. So all of these experiments are using one of those techniques to try and look for dark matter. The really clever experiments are using two of these techniques simultaneously. So for example, CDMS looks for both the deposition of a heat-like pulse and an electrical pulse at the same time. Using two different methods at once, as you might imagine, gives you a much better handle on what it is you're looking for. After all, I want to make sure that I don't just see a blip. I want to make sure that that blip is dark matter and not something else. We don't know yet which of these experiments is the best, which technique is the best, and which one is going to make the discovery. And so it's good that all these people are competing, because if we had to do these sort of one at a time, it might take us 100 years to figure out the right way to do it. So let me go back to CDMS. I said this is the one that we're involved in at Fermilab. We're not doing it at Fermilab, and the reason we're not doing it at Fermilab is if you take a detector like that and you put it on this table and you turn it on, you'll see lots of blips all right, but they're coming from natural radiation and from cosmic rays. So that's completely hopeless. So unfortunately for us, you have to go do these things down a mine somewhere. And in this case, it's being done in the Sudan mine, which is an iron mine in northern Minnesota. A place that always looks like this. It's a frozen waste. I grew up in Minnesota, so I can vouch for the fact that it's a frozen waste. It is much warmer when you go down about 2,000 feet, so maybe that's a good thing. And here's part of the collaboration. Actually, I think this is down in the mine, very hard to. So you go down the 2,000 feet in the mine. That gets away from most of the cosmic rays, which is one of the things that will make a false blip in your detector. You then have to construct these very sensitive detectors. So what you're seeing here on the upper right is part of the CDMS detector. So one thing you notice is that it's not very large. We would like it to be larger, but these detectors are very sensitive. It's very difficult to put together these very sensitive detectors. You only have so much money to do it. And so we build them as big as we can, but with a limited budget, we're still talking about reasonably small detectors. But as I said, there's lots of dark matter particles going through your body and going through this even reasonably small detector. So it doesn't mean you won't see a signal with a small detector. The other thing you have to do with this detector is you have to cool it down. CDMS runs at about 1/100th of a degree above absolute zero. So that sounds hard, but nowadays it's actually, well, I call it a piece of cake. I wouldn't actually know how to do it, but for people that know how to do it, it's a piece of cake. So you go down 2,000 feet in the mine, you build this incredibly sensitive detector, you cool it down to 1/100th of a degree above absolute zero, and then you let it sit for 6 months, and then you see what kinds of blips you get. Now, even though we've done all of these amazing things to try and prevent this experiment from seeing noise or seeing things that aren't dark matter, there's really no way around the fact that most of the things that you will see, most of the blips in these very sensitive detectors, are not dark matter. And you actually know some of the reasons for this. It doesn't matter how far I go down in the mine, the rock in the mine is radioactive at some level. So you can't get away from that radiation. In fact, the material in the detector or in the thing that holds the detector is slightly radioactive. Your body is radioactive. Everything's radioactive at some level. There's also radiation in the air. There's radon gas. It's the same thing that leaks into your basement and kills you. You can't get rid of all this natural radiation. And the cosmic rays, although you can get rid of most of them down the mine, there's lots of cosmic rays. Some of them are very high energy particles. Nature has a very large budget for particle accelerators and makes very high energy. So you can't get away from that stuff. But as I said, the CDMS detector, in addition to being very sensitive, it detects dark matter blips in two different ways. And because of that, and also using fancy things like very precise timing, they're able to tell the difference in a very convincing way between this kind of what we call background radiation and the thing they're actually looking for, which are these WIMP dark matter particles. So at the end of the day, what they will show, and this is not just the latest results, I think these are results that I'm not supposed to show. So they're preliminary sensitivity projections for this experiment. And the way they make these plots is they say, okay, let's look for some blips that would be dark matter, eliminate all the things that look like they're ordinary radiation, and then do we have anything left over that could be dark matter? If you don't have anything that looks like a dark matter blip, then what we do is you set what we call a limit. So you say, okay, so now I know that the dark matter doesn't have certain properties. And what do I know? Well, you have to do this as a function of two things. Because how many blips you would see would depend on what the mass is of the dark matter particles. And it also depends on how much the dark matter particles interact with ordinary matter. And we don't know either one of those things. So when I don't see something, I can then say, well, if they interacted at least this much with ordinary matter, and if their mass was in a certain range, then I would have seen them. And since I didn't see them, I can rule all that out. And so in these curves here, everything above the curve means that the dark matter particles, if they interacted at least that much, we would have already seen them, and therefore they don't do that. They must interact even more feebly than what's shown on this plot. So as these curves go down and down and down, what you're doing is you're looking at more and more weakly interacting possibilities for dark matter. As we'll see at the end of this talk, theories that predict what the dark matter particles are, like supersymmetry, tell you sort of what are the interesting parts of this plot. And the only thing I want you to really take away from this plot is that these CDMS sensitivity curves, so far they haven't seen a signal, so these are just ruling out things that could have been there. They're ruling out a whole bunch of that shaded region, that shaded brown region, which is where we theorists told them they ought to start seeing dark matter particles if they are produced by a theory like supersymmetry. So we're not just ruling out any old dark matter particles. We think we are now getting to the sensitivity where we should see dark matter particles of the type that seems sort of most natural from a theoretical point of view to be there. And of course that may mean that we'll have a discovery. We could have a discovery this year. They're running this experiment right now. You may wake up 3 months from now and there'll be an article in the paper saying dark